In this highlight video, we will talk about our second electrophilic addition reaction to alkenes, and that is the hydration of alkenes. The hydration, like I mentioned before, is simply the addition of water. This reaction, therefore, is simply the reverse of the dehydration reaction that we talked about before. So after you've watched this video, you should be able to predict the products and mechanisms for the addition of water to alkenes. We're going to pay attention to the regio and stereoselectivity of the reactions. So we add water to an alkene and nothing happens. So, what do we have to do? If we add water, but we also add a small amount of sulfuric acid, then we get a reaction. So why do we need the acid? Well, the reason is that the first step of the electrophilic addition reaction, just like when we were adding HBr, HCl, is the protonation of the double bond. And water is simply not a strong enough acid to protonate that bond. And so we need a stronger acid. Once we do that, the reaction will proceed as we would expect. It's going to follow Markovnikov's rule, so we protonate at the position with more H's. Once we form the carbocation, this reaction is essentially like an SN1 substitution, because now we can have our water molecule react with the carbocation to give ourselves a protonated water molecule here, or a complete water molecule. And to get to a product, we need to deprotonate that. And we can use the conjugate base of sulfuric acid. Goes like this. And we get to our final product that has an OH here. Alright, so note that this is simply this mechanism. In fact, we should draw all of these steps as being reversible. And this reaction is just the reverse of the dehydration reaction. Right? In the dehydration, if we start here, the first thing we do is protonate it to form our water molecule, which is a good leaving group. That can come off to form the carbocation, and then we lose a proton from the beta position to go to the alkene. So exactly the same mechanism, but in the reverse direction. Let's think about what the reaction energy diagram would look like. So again, we're going to have a starting point. This is our alkene. We're going to generate a carbocation intermediate, which is going to be higher in energy. We're going to generate then this protonated species here, which is going to be still above the starting material, and then our final product will be the lowest. So we're going to have a rate determining step is protonation of the alkene. We then add the water molecule, and finally we do the acid-base step. Okay, so this is the carbocation. This has the water molecule attached. And this over here is our final product. All right. Instead of just adding water, we can also add alcohols to alkenes. And we can understand this by considering that if we compare water to an alcohol like this, all we've done is remove one of the H's and added this alkyl group. The other H is still here, the one that we need to lose by deprotonation in the end. So let's take a look at how this mechanism would go and show us what our product will be. Okay, so the first step is always protonation of the alkene. It's going to protonate at the position with more H's to give us the more stable carbocation, following Markovnikov's rule. Now in this case, notice that we have a secondary carbocation. We have a more highly substituted center right next to it. So this molecule would likely do a 1,2 hydride shift. To give a more stable tertiary carbocation, which can then react with the alcohol just like a water molecule would. To get this intermediate that has the intact alcohol attached. And then we have a final step where we have the conjugate base of sulfuric acid, remove that proton. And that is going to give us our product. And notice when we start with an alcohol, our product is an ether. All right, so I see a mistake. This step shouldn't be protonating by the alcohol, right? Alcohol is not a strong enough acid. So this is going to get protonated from the acid like this. What if we don't want a product that follows Markovnikov addition rules? What if we want the OH at the less substituted side? We want the reverse product, the anti-Markovnikov product. All right, if we want that, we're going to use a reaction that's called hydroboration oxidation. It's a two-step reaction. To do the hydroboration part, we use, this is borane. And borane is going to add directly to the double bond. It's going to align itself with the hydrogen-boron bond parallel to the carbon-carbon double bond, with the H pointed toward the more substituted side. Now the pi bond can attack the boron. This is essentially a Lewis base, Lewis acid reaction because borane is a good Lewis acid. But in the same step, a hydride is going to move to the more substituted side. This is a concerted step. right? We talked about that before. Concerted means that all of the bond forming and bond breaking is going to take place simultaneously. So because of that, though, the H that ends up attached and the boron, it's going to be a BH2 group here, are both on the same side. So this is what we call a syn addition. It means the two groups will be on the same side. And in a final oxidation step, the borane, this BH2 group, is going to be converted with hydrogen peroxide to an OH. And we're not going to worry about the mechanism of that, though what we want to pay attention to is that there's a retention of configuration here. This is retention, and the addition is overall a syn addition. So notice that our product, right, is, the reaction is regioselective, because it does an Markovnikov addition, meaning that it adds in the opposite orientation as a Markovnikov addition. The reaction is also stereoselective, because it does a syn addition, meaning that the new OH and H are on the same side. Let's do a few more examples. The first one, we have water and sulfuric acid, so we're doing an acid-catalyzed hydration. So the first step would be to protonate to form the carbocation at a more stable position, and the alcohol would end up at that position. So let's just write our products. Remember that this methyl group up here at the top is remote to the reaction, so it would always stay the same. Now the alcohol, or the water nucleophile, can come in from the top or the bottom, so we're going to end up with two stereoisomers. If it comes in from the top, we'll end up with an OH here and the methyl group going back. This one stays the same. If it comes in from the back, the methyl group will be coming forward. So these two are stereoisomers, and they are, what's the relationship here? They are diastereomers. And remember, whenever we form a mixture of diastereomers, the reaction will likely be stereoselective, because the pathways to those two diastereomers are going to be different in energy. Okay, is this reaction regioselective? Yes, the reaction is also regioselective because it follows Markovnikov's rule. What about the next one? This is a hydroboration oxidation. So remember, this reaction is going to follow an anti-Markovnikov addition, and it's a syn addition. So likewise, we're going to end up with a mixture of stereoisomers here. So the alcohol is going to go here. So if it comes in from the top, the new H will also come in from the top, pushing the methyl group back. The other possibility is that the OH comes from the back, giving us the H on the back because those are syn, and the methyl in front. So again, just like the example up above, this reaction is regioselective because the alcohol only comes to this position, not to this one. And it is stereoselective because it's doing this syn addition, and we're getting only 2 of 4 possible stereoisomers. The other 2 would be with the OH pointing up, but the methyl group pointing forward as well, or the OH back and the methyl group back. Right? Those would be 2 other possibilities, and we're forming 2 out of 4 possibilities. Let's look at the last problem. So in this case, we have an acid-catalyzed reaction. We're going to add an alcohol to the double bond. So in this case, we're going to protonate. We have to figure out where is going to be the more stable carbocation, or if one is going to be more stable than the other. So we have 2 possibilities. One where the new H goes here, leaving a plus at this position, secondary carbocation, or the new H would go here, leaving the plus at this position. So, do we have a difference in stability of these 2 carbocations? Yes, in fact we do. The one on the right, because the plus charge is adjacent to the benzene ring, that plus charge can be delocalized inside the benzene ring, and so this one has resonance. So it's going to be the major one. We're not going to form this one, and so our product is going to add the alcohol to that position. So we're going to have an alcohol here. We just look at our alcohol, see what's attached. It would be like this, and because it can come from the top or the bottom, we are going to have a racemic mixture. Okay, so this reaction is regioselective, but not stereoselective. Because we're getting a mixture of stereoisomers.